Okay, we are live. And so good evening and welcome to the North Jersey Astronomical Group. This is our October meeting, and thanks for joining us tonight. And whoops, hold on one second. I'm getting a little bit of feedback here. Hold on, there we go. That's better. So welcome to our meeting. Tonight we have a presentation that we're going to be doing for you all about Buzz Aldrin, New Jersey's favorite astronaut. And so we've got Chris Mauro, our vice president of our club, is going to give this particular presentation. And following the presentation, please stick around. We will have a little tour of the nighttime sky. Mark Zdarsky, our chair of our observatory committee, will be giving a little tour of what's visible in the nighttime sky right now, and that will be followed by our business meeting. So I think without further ado, let's turn things over to Chris, and he's going to tell us all about Dr. Rendezvous. And so, Chris, take it away.
Okay. Just let me know if the volume is fine. Okay, let's see.
Yeah, that's good.
Okay, I'm doing a share screen. Let me see if I can get the slideshow started. Okay, can everyone see that? Okay. Thank you, Kevin. Can everyone see the screen? Is that coming through? Okay, I see some nodding heads. That's good. Okay. Good evening. Thank you for attending. I'd like to give a special thanks to Dr. Mary Lou West for her, never-ending support and encouragement with these projects. I want to say thank you. I hope this talk will give you a little deeper appreciation for the science and the complexity of spaceflight. Last year, we celebrated the 50th anniversary of the first human landing on the moon. And that exploration continued through 1972. And this is the lunar rover. We actually, we had to bring our own car. There weren't any dealers out there. So that certainly gave people, different perspective on the lunar landscape. And we really hope to be able to go back and put some new footprints on the lunar surface. So when we look at the Apollo mission, in 1962, the conversation at NASA centered around the flight plan for the mission. We really couldn't begin designing until we knew what we were building and how it was expected to perform. Many alternatives were debated, and eventually NASA engineer John Houbolt persuaded Werner von Braun and others of the benefit of using a lunar orbit rendezvous approach. This orbital maneuver was theoretically feasible, but as yet untested. Around the same time, a former fighter pilot and Air Force wing commander, 33-year-old Buzz Aldrin, prepared and submitted his doctoral thesis in January 1963 on line-of-sight guidance techniques for manned orbital rendezvous. He was thereafter known as Dr. Rendezvous, and the dedication of his thesis, I think, is worth reading, somewhat prophetic as well. It says that in the hopes that this work may, in some way, and I have the group of people here. Hold on, some way may contribute to their exploration of space. This is dedicated to the crew members of this country's present and future manned space programs. If only I could join them in their exciting endeavors. Okay, something's not right here. There we go. Okay. And he was thereafter known as Dr. Rendezvous, and he would fly on Gemini 12 and Apollo 11. So the problems, the statement in a sense, is being able to perform a rendezvous maneuver and then eventually a docking maneuver. So the Gemini program was designed to prove completion of three essential objectives. The first was long duration spaceflight, because the trip to the moon and back was going to take 10 to 12 days. extravehicular activities. You need to be able to get outside of your spacecraft with the life support systems. And of course, the rendezvous and docking that was essential to the entire flight plan. So the basic rendezvous maneuver can be described this way. You and another spacecraft are in orbit and at the same altitude and at the same plane, and you trail the other craft by 5 kilometers. So what do you do to catch up and dock with that craft? And how do you do that? And it's still very relevant today, for the space station, because, we dock with the space station on a regular basis. As a matter of fact, today I just recently saw this was the supposedly the last launch from the Russian launch location for an American to go to the space station. So before we can solve the problem of rendezvous, we need to discuss fundamentals of orbits and orbital mechanics, beginning with what is an orbit. Okay, it's a good place to start. So the orbit is a path of an object where each point in the path, its centrifugal force is equal to its gravitational force. So essentially it's in a state of free fall. And so if we look at some of the equations related to that, we have the force of centrifugal force is the mass times the velocity squared over r. The gravitational force is the gravitational constant times the mass of the Earth, the mass of the satellite, divided by the square of the radius. And the radius is measured from the center of the Earth, not the distance above the Earth. Now, if we take and we make those two equations equal, we come up with a couple of interesting equations. The main one is the velocity in orbit. So the velocity in orbit is the square root of the gravitational constant, mass of the Earth, divided by the radius. So to boil that down pretty quickly, it kind of equates to an orbital velocity of about 17,500 miles an hour, or about 4.85 miles per second. So a couple other things come from this. Number one, the velocity of the object in orbit is not dependent on the mass of that object. So it doesn't matter how large or big the object is. Could be the space station. It could be, Sputnik. The orbital velocity is a function of the mass and gravitation and the distance from the center of that mass. So as the radius of the orbit increases, the velocity decreases. Excuse me. So I think those are the two important things to understand from the formulas for orbital velocity. So if we look at an orbit of a satellite in low Earth orbit, about 100 miles above the surface, you would be traveling at 17,500 miles an hour. And think about that for a moment. You're on the Garden State Parkway at intersection of 280, exit 145, and then 1 second later, you're at Hoover Avenue, exit 150. That's how fast orbital velocity is. It's truly amazing. So the first step is getting into orbit. And this is a shot of the space shuttle being launched. So assuming you have enough thrust to get into orbit, the where, when, and how you launch is critical. The where component is your launch site, and you don't have a lot of variability in that. And what that does, your launch latitude is the primary determinant of your angle of inclination, the inclination of the orbit. Assuming that you launch at a 90-degree launch azimuth, generally in an easterly direction, whatever latitude you're at, that's where your orbital inclination will be. So I've listed a couple of sites around the world. There are many, many sites. Some of them are not capable of achieving orbital or even lunar launches for that matter. But in these major locations, you see the United States, we have two, the Kennedy Space Center and Vandenberg give us two different orbital inclinations. European Space Agency is a little closer to the equator. They use a site in French Guiana. The Russians, of course, Baikonur Center at 46 degrees north. China, India, and Israel. A couple of points. The International Space Station is at a 51.5 degree inclination. And basically it was intended to put it in that orbit so that the Russians would have, less objection to participating in the International Space Station. So that helped a lot. Some countries need to launch in a manner to avoid booster rockets falling on politically unfriendly countries. So for example, Israel launches in retrograde orbits, at least they leave any debris on, in unfriendly territory. And the reason that we did decide on a 51.5 degree or inclination for the space station is that it's very costly to change your inclination. We'll see later when we look at how you change orbits. It can cost almost as much as a translunar injection to change from a 20, some odd degree orbit to a polar orbit. The when is determined by the launch window, and that's a calculation made based on what your objective is. So if your objective is to dock with the space station, you have to pick a time where you can perform the number of rotations in orbit that you need, adjust to the proper inclination, and then be able to dock. And that's all determined by your launch window and what your objective is. The how incorporates all the other variables, including the launch azimuth, which is the direction at launch. You can launch off 90 degrees by a certain amount, but in general, you're launching in an easterly direction because you take a prograde orbit around the Earth, except, as I mentioned, for Israel. So atmosphere, what a drag, okay? And all orbits below 600 miles must consider drag. It causes orbits to decay. The atmosphere has layers. As you can see, the primary layers are the troposphere, the stratosphere, then follow the mesosphere, thermosphere, and exosphere. The upper limit of the exosphere is about 10,000 kilometers or 6,200 miles. And at that level, it merges with the solar wind. Lower bands of the thermosphere from 50 to 620 miles are where most satellites live. It's cloudless and free of water vapor. At this band are also the Aurora Borealis, as well as the Van Allen belts between 400 and 36,000 miles, and the ionosphere, which bridges both the mesosphere and the thermosphere from 37 miles to 620 miles. Back in the 60s, we were able to confirm what's called a Kármán line. The Kármán line was first calculated by Theodore von Kármán, and basically it defines a point where the atmosphere is too thin to support aerodynamic flight. It occurs at approximately 100 kilometers or 32 miles above the Earth's surface. In the 50s and 60s, 1950s and 60s, the US X-15 aircraft reached the edge of the Kármán line, establishing the highest aerodynamic flight at 108 kilometers or 67 miles. It also set the world speed record of Mach 6.7, 5,140 miles per hour. So when we look at orbital decay, at 500 miles approximately, the orbit will decay in decades. At 370 miles, it degrades in years. So an example, we look at the space station. It's almost a circular orbit. Its inclination is 51.5, as I mentioned. It's 254 miles above the surface. It loses between 50 and 100 meters per day in altitude. That's about a mile per month. However, it does have rockets that it can restore it to the desired orbit that it needs to be in. The Hubble, on the other hand, does not have rockets. In 2015, it was orbiting at 315 miles. And then in 2018, it's orbiting at 340 miles. So it's losing 13 miles over 3 years. And eventually will, probably fall into the, further in the atmosphere or move to another layer or another level where it can still be functional, possibly. So let's use a little more mathematics to begin with before we talk about rendezvous. So the conical shapes are fundamental to geometry, and we all know them pretty well. The circle, the ellipse, the parabola, and hyperbola. I think what's worth looking at is a diagram that I found that puts these shapes over a gravity well. And what's kind of interesting about this, if we look at the two, the parabola and the hyperbola, you notice that they extend beyond the gravity well. The ellipse on this side here and the circle are within the gravity well. The parabola and hyperbola are outside, because those are escape trajectories. Those are trajectories that if you add enough velocity, you can escape the gravitational pull of whatever you're bound by. So the difference between them, what differentiates them is the eccentricity. So eccentricity is a mathematical dimension, which we'll talk about a little later. For a circle, it's zero, exactly zero. For an ellipse, it's greater than zero, but less than one. Hyperbola is equal to one. Parabola is equal to one, and hyperbola is greater than one. So with that, we can jump to Kepler's 3 laws of planetary motion. Okay. He based his 3 laws on observations that Tycho Brahe had made in the, I think, 15th century. All orbits are elliptic. That's the first law. Second, orbit sweeps equal areas in equal time. So here we have 3 areas, A1, 2, and 3. They are all geometrically equal. So the object in orbit would travel from A to B in the same time it would travel from C to D and E to F. But you notice something interesting. There's a longer distance in A1 and a little less in A2 and less in A3. So obviously, it's going to travel faster in this portion of the orbit than in the far portion of the orbit. And that's a very important piece of the calculations for when you're trying to do rendezvous and docking. The third law is that the orbital period, the time it takes to complete one orbit, is proportional to the semi-major axis of the orbit. We'll define that in the next couple slides. So you can see this is Kepler had an uphill battle. So he says here, you see the orbit of a planet is elliptical, and his comrades are saying, well, first, what's an orbit? And what's a planet? And what does it mean to be elliptical? Okay. So when we look at an ellipse, there are a number of parameters. So by definition, you have 2 foci, 2 points of focus, unlike a circle, which has 1 center focus. And the definition is that the ellipse is a path where the sum of the distances from each foci are constant. So the R and R prime at every point in this ellipse are equal, and they are the same constant number. The major axis is the longest diameter of the ellipse, which passes through both foci, as well as the center point. That's the major axis. Half of the major axis is the semi-major axis, and this is used in many of the formulas for the period of an ellipse, as well as other required dimensions. The minor axis, which is the perpendicular to the major axis, also runs through the center. So you can see the B dimension is the semi-minor axis. The eccentricity is a function of the elongation of the ellipse. So this value here, which is A times E, and remember, E is going to be a value between 0 and 1. It's going to have an effect. The bigger E is, the more elongated the ellipse will be. So based on this, you can derive or calculate the formulas for velocity at any point in an elliptical orbit, as well as in a circular orbit. And you can calculate the formula for the period. So you can see here again the rules for orbit. The velocity of an object in orbit is not a function of the mass of the object. The velocity of an object in orbit changes inversely to its distance from the central mass. So the further away it is, the slower it's going. The time it takes an object to complete an orbit is proportional to the length of the semi-major axis. So the larger the orbit, the more elongated the ellipse, the more time to orbit. So, we've talked about a number of things that also affects other countries. You could see that many countries are putting satellites in orbit. They were launching at different times. So the spacefaring nations have come up with this geocentric equatorial coordinate system. So it's a system of defining an orbit around the Earth. And it includes a number of different variables. So we'll talk about each one of these. So the first one is the semi-major axis of the orbit. And if I can find my mouse, here it is. So you can see that that's this distance here. That's your semi-major axis distance. The eccentricity, as we mentioned, determines the elongation of the orbit. The inclination, that's the iota angle, which is determined where the orbit path crosses the equatorial plane. So this is your reference plane, is the equatorial plane. Another reference point is your x-axis. Your x-axis points to the point where the vernal equinox occurs. So this is all relative to Earth motion. The fourth quality is the right ascension of the ascending node. So in an orbit, if you go from south to north, you are cross the equatorial plane. That's your ascending node. The descending node would occur where you go from north to south. Algebraically, you would look at it as the z-axis. So you're going from negative z values to positive z values. That's ascending node. Versus positive z values to negative z values is descending node. So this angle omega from the x axis to the point of the ascending node, that's the right ascension. The next parameter is the argument of perigee, which goes from this point where the right ascension occurs to the point of perigee. So that would be the closest point to the gravitating body. So this angle of lowercase omega goes from your right ascension point to your perigee. And the last item is the period or time of the orbit. So with this data and information, you can quantify and calculate the position in this orbit at any time. So again, we need to talk a little bit about the different types of orbits before we can hope to rendezvous and dock with an object in an orbit. So there are a few different types. First one is pretty obvious, a circular orbit, which occurs at various altitudes. There are geostationary orbits, which are stationary over the equator. So these are orbits that have to be adjusted from their launch point so they have a zero inclination to the equator, the equatorial plane. There are geosynchronous orbits, which vary a little bit from the geostationary in that they're not over the equator, but they are over the same spot on the Earth. These orbits are in the area of 22 to 23,000 miles above the surface. And so they are very, large orbits, generally circular, and as I mentioned, they're over the same spot. The next is circumpolar orbits, and they can be anywhere from around 100 to 150 to 1,500 kilometers in altitude, and you can see that the orbit, or I should say the path over the Earth changes. So the satellite is orbiting and the Earth is rotating beneath it, so you can get a view of pretty much every spot on the planet with the circumpolar orbit. There are sun-synchronous orbits, which are near polar. They precess by about 1 degree per day, which results in the fact that you can then be over the same spot at the same time every day. And the altitude of those orbits is between 700 and 800 kilometers. The next are highly elliptical and elliptical orbits. This is a good example of a very highly elliptical orbit. And probably the best application and commercial use of it is the Russian communication satellites are in what they call the Molniya orbits, and they have a number of satellites in those kinds of orbits, very elongated, elliptical. The apogee of those orbits is around 22,000 miles, pretty close to the geosynchronous altitude, and the perigee is between 1,500 and 200 kilometers. Also adopted by spacefaring nations is a understanding of the altitude classifications for satellite orbits. So this diagram shows the orbital velocity at different altitudes. It also shows the predominant satellites like the International Space Station, Hubble, and so on. And probably the most interesting piece of it is a graveyard orbit. So this is an orbit where old satellites that are non-functioning or close to none or totally dated are put into an orbit beyond the geostationary orbits, less affected by drag. And at this point, they're just sitting out there in long duration orbits, hopefully not bothering anybody. I'm not sure what they're going to do later on with these things, but it's too costly to have them re-enter. It requires too much fuel, so it's easier to move them from where they are up to this graveyard orbit. So now we can talk about orbital mechanics. And this is significant because in order to rendezvous, you need to be able to change your orbit, the altitude, and the velocity. So how do you do that? Well, you have to either add velocity or reduce velocity. So the velocity generally is called a delta V. If you listen to a lot of the conversations with spacecraft, they'll talk about delta V and, adding certain amount of feet per second or whatever the appropriate dimension is for what they're doing. So adding velocity at a specific point in the orbit, at this point here, accomplishes the following. It raises the altitude of every single point on the orbit until it comes back to the original site where the burn occurred. So you can think of it as extending the apogee of an orbit, but eventually it will return to the same spot where the burn was initiated. Okay. The opposite is true if I take away velocity. And here you can imagine if I reduce my velocity at this point, I fire retrograde, I'm going to create a orbital path that will reduce my perigee. It will fall into this area here, but again would return to the point where the burn began. So these two things, if I add speed, I gain velocity. Excuse me, if I add speed, I gain altitude. I lose velocity at this point in the orbit. At this point here, if I do the reverse, if I reduce my speed, I lose altitude in the perigee, but then at that point I'm going faster. So there's like a little bit of a counterintuitive notion to this. I add velocity, I increase the altitude, which causes my orbit to slow down. If I reduce velocity, I lower my orbit, which causes my velocity to increase. So the first transfer to talk about is Walter Hohmann transfer orbit. He devised this process in 1925. And he was a member of the same rocket club as Wernher von Braun, by the way. And this showed an efficient way to change from one circular orbit to another circular orbit. So you start out here, that's your original orbit. Your target orbit is this orbit here, okay? So you fire, adding velocity, which gives you altitude, okay? Slows you down, but it gives you altitude. And then 180 degrees afterwards, at this point here, you fire again, adding velocity, which now raises, remember, adding velocity raises all the points in the orbit, except where you do the burn. So now you've created an orbit that's a little bigger. So this is called a Hohmann transfer orbit. And this is still used today for many, many missions. Excuse me. There's something called a geostationary transfer orbit. So this is the orbit that you use to get to a geostationary level. But also, it's used for the Mars lander, the InSight lander. So this was launched in 2018. And you can see this line. This is a Hohmann transfer orbit that was used to put this into the vicinity of Mars. There's also a bielliptic transfer. So Ari Sternfeld in 1934, he devised and calculated a three-step maneuver that was more efficient for very highly elliptical orbits. So if you have a change of orbit where the ratio of the semi-major axis is greater than 11.94, the bielliptic transfer is more efficient. Another little note, Ari was a pen pal of Tsiolkovsky. So the community knew each other. So in this maneuver, you start point number 1, add delta V, created a very wide elliptical orbit. At the point number 2, you add a little more velocity. Remember, if I don't do anything here, I'm going to come back on this inside. I'm going to return to where I did the original burn. So I add a little more velocity here, and now raise my my perigee at this point. And then the third burn is actually retrograde. So that now lowers the other parts of the orbit. And so I end up in this new orbit from here at this point. So if these orbits are far enough apart where the ratio of the semi-major axis is great, then this bielliptic transfer works. So another way to change orbits, and it was the Oberth effect, first calculated by Hermann Oberth in 1927. And he calculated that the increase in kinetic energy resulting from a rocket burn is greater at high speed than lower speed. So by firing at let's say a perigee where you have higher velocity, will elongate the orbit and eventually bring you to your target orbit. And this process has been used. This is the Indian lunar probe, the Chandrayaan-2. And you can see each time it comes around close to the Earth in perigee, it gives a little burst, a little more energy, and eventually driving it out toward the orbit of the moon, where it was supposed to land. I'm not sure that it was successful, but that was the objective. And lastly, another orbital change is changing orbital inclination. And this is a very complex and costly maneuver. All maneuvers discussed to this point have been either prograde or retrograde tangent to the orbit and the direction of flight. To change the inclination requires thrust at an angle to your direction of flight. And as we talked earlier, they're expensive maneuvers. Changing the inclination from 28 degrees to a polar alignment of 90 degrees can use as much fuel as required for a translunar injection. And the burn needs to be timed for the intersection of the node point where the current orbit intersects the target orbit. So here's an example. So if I'm, on this inclined orbit here, and I want to be on an equatorial orbit, I need to fire in this vector, and you need to calculate how much you need to fire, but that will flatten out the orbit and make it elliptical. Same thing is true in a polar orbit, changing from a non-polar orbit, non-90 degrees, to make it 90 degrees. So let's go back to the problem of rendezvous. So you trail the target vehicle by some non-trivial amount, and you orbit in the same plane, and you're at the same altitude. So we've learned that if you increase the speed by firing in the direction of your orbit, you increase your apogee and the altitude 180 degrees after the burn. And also your velocity decreases due to the change in altitude. So you've traded speed for altitude. If you decrease speed by firing in the opposite direction, you decrease your perigee, and as a result, your velocity increases to change the change of the altitude. One way we can think about this as mere mortals on the planet, we have basically you slow down to speed up and speed up to slow down. And think of it as think about NASCAR and roller derby. So here we have an inclined plane, which sort of kind of simulates a gravity well. But if you want to catch or pass somebody, what do? You drop to a lower orbit, on the plane, and as you increase your speed, and then you can catch and pass, somebody who's in a higher orbit. So that's essentially what you try to do. Now, rendezvous is not as simple as it sounds. One of the first Gemini missions, they tried doing line of sight only rendezvous, and they failed. They couldn't even come close. So it was not until they were able to put radar and the computer programs were operational that the rendezvous and docking became truly feasible. Rendezvous is essentially putting your craft on a collision course with an intercept approach vector, and then closing that range, having a decreasing range. I think of two boats on a collision course is one way to think about this. So if you're a sailor, when you have a constant bearing on another craft, you're on a collision course because you're closing that range. So you can just kind of imagine this not on the surface of the Earth or in the water, but imagine this in 0G in orbit. So now we get to Aldrin's thesis. Okay, this is why he was called Dr. Rendezvous. He submitted this line of sight guidance techniques for manned orbital rendezvous. He had a couple of assumptions that were defined in the abstract and in the beginning of the document. It's a 330-page document. It's quite technical. I'll show a couple of diagrams that you can see. So all motion of the target is from the point of view of the interceptor. He uses these interceptor and target, I think, probably mostly out of his experience as a fighter pilot. So that would be kind of a similar terminology he'd be used to. He assumes that you have a means of measuring the range, the rotation of the craft, the phase angle, and the phase rate. The phase angle and phase rate can be thought of the followers. If you think about backing into a parking spot, depending on where you are and how far you are from the entrance to the parking spot, you may have you're going to have a different curve that you're going to take. You're going to steer in a different way. So the phase angle talks about that angle of curve, and the phase rate is how quickly you're changing that phase. So it's one way to think about those those parameters as one craft is approaching another one. He also assumes that all initial positions are based on ground tracking, which works in the Gemini program, not necessarily in the Apollo, because they might be out of line of sight, and also with the distance involved. By the time the information is communicated from Earth to the Moon, things have changed. And that after the initial correction for guidance, guidance is then in the interceptor only. So this is kind of focused more on the Gemini program. So also in his document, he talks about bioelliptic orbit changes, about coplanar and Hohmann orbit changes, and he defines the phases of lunar orbit rendezvous, beginning with launch, and then into a temporary, and then a parking orbit, and then finally obtaining line of sight and determining an intercept path and entering what he calls the terminal phase, which finally ends with velocity matching, where you match velocities with the target vehicle. Okay. He also talked about the radar and optical material that they would use, as well as computer guidance And he did talk about a lunar landing abort, if necessary, and then being able to rendezvous back with the command module. So here is one of the diagrams from the thesis. I won't take too much time with this, but he starts with a launch from the Earth. This is Gemini, so we're going in a posigrade orbit here. We reach a orbital altitude of about 130 nautical miles. So that's his parking orbit, okay? From there, he moves to a waiting orbit, which brings you a little closer to the target. Finally, he has a line of sight where he picks up the target, enters a transfer orbit that merges with the target in 90 degrees. So this is a little faster, a little closer than the Hohmann transfer orbit. In his document, he makes it pretty clear that he prefers what they call coplanar orbits. So these orbits are all in the same plane. It makes better use of the line of sight guidance, as well as the rendezvous point can be adjusted. So the intercept phase, which I'll show here in a minute, the intercept phase could be delayed until the target is observed. So here, this is a lunar example. It doesn't come from his thesis. This is from another source. So this is retrograde. So you see that you launch from your landing site, you go into the first waiting orbit, or excuse me, parking orbit. You do a couple of burns here and another one here where you maintain constant distance from the target orbit. And then finally you do the terminal phase initiation burn. And that is what brings you into rendezvous. Okay. So here's a picture of the line of sight radar. And this is not through the LEM, this is through the shuttle. But the LEM was very similar. It had like a target on the window. The windows were actually quite small. They were about 5 inches by 13 inches. So they weren't that big, but it did allow being able to establish line of sight. From that point, you would put the parameters into the computer. And again, if you listen to the dialogue, of the lunar landing, Aldrin makes reference to the computer telemetry, and that those are the numbers that he's giving Armstrong as they approach. Boy, excuse me. So this alignment is a critical point to establish any rendezvous. And then the terminal phase. This is the lunar module approaching the command module in the terminal phase. And the objective is to line up for docking. And there are small thrusters. Again, all of the work is being done by the lunar module. It has a smaller mass. The fuel is more efficiently used in a smaller mass than trying to change the attitude of the command module. Unless it was an emergency situation, you wouldn't move the command module to meet with the lunar module. And then they use small thrusters to slowly bring the lunar module in and then through the docking port. So Aldrin uses these, I just put this up here for information purposes. I'm not going to discuss them. He uses these differential equations that were programmed into the computer, and these were devised by Cloesi and Wilshire. And they're linear differential equations that describe the motion of both the target and the interceptor in circular and elliptic orbits. And rendezvous were able to be accomplished within 270 degrees. Course corrections were made by the computer every 60 degrees, with the last being made at 30 degrees. And so Aldrin certainly has left his mark on the Apollo with all of this background work. There's always room for improvement. And so David Scott, who was the 7th man to walk on the moon, and James Irwin, the 8th, devised a shorter docking. The original rendezvous and docking took about 4 hours. It was a pretty lengthy process. This pretty much cut it in half, saved about 2 hours. So here you would launch, you would kind of almost immediately go into your waiting orbit, and then do this terminal phase initiation burn, and then eventually rendezvous. And you could do that in a shorter period of time. So what are some of the observations of this process? I guess the first that struck me is that the exploration of the solar system and the other stars is very complex. It's not like watching a sci-fi movie. That's for sure. The exploration of space is a community effort. When you see the people who have been involved and who have contributed to this effort, they come from all different backgrounds. They come from all different countries. This is not like somebody, forging out through the wilderness and doing exploration. And it's also essential to manage undefined contingencies and margin of error. We learned that with a number of the catastrophes that we've had, and with some of the successes. Apollo 13 being considered a success, not a failure, because we were able to solve the problems. But it's important to manage these contingencies. You have to engineer for safety, and you have to balance cost. All of these processes and maneuvers, have a cost, and in most cases, they allow for a 10% to 15% contingency in terms of fuel. So these maneuvers are precise, the timings are very precise, and you're constantly monitoring how much fuel you have used and have left. So a lot's happened since Copernicus first completed his work on heliocentrism in 1532, just about 500 years. And of course, then you have Galileo and Kepler and Newton. And now we get to the 20th century, we have Tsiolkovsky with the rocket formula, Goddard with liquid fuel rockets, Hohmann with the Hohmann transfer orbit, Oberth and the Oberth effect. We have von Braun. And I wanted to add a couple more people. Katherine Johnson, you probably remember her character from the movie Hidden Figures. And Margaret Hamilton, not to be confused with the author of Gone with the Wind. She was the program lead and project manager for over 300 people who wrote all that code. That's all the code listings for the computer that was used on Apollo. And now we have Buzz Aldrin. Sometimes it does take, it takes time to recognize the lasting contribution that an individual makes. And here, we have Aldrin, fighter pilot, a scientist, a scholar, an astronaut, and an explorer. He was born on January 20th, 1930 in Glen Ridge, lived in Montclair, attended Montclair High School, played football and was coached by Clary Anderson. He was third in his class at the U.S. Military Academy, received his wings in 1952, had 2 confirmed kills in combat in Korea, was awarded the Distinguished Flying Cross. He was the commander of a F-100 fighter squadron in Germany. He entered MIT in 1959 and completed both the master's and PhD program in astronomics. He was the co-pilot on a Gemini 12, completing 3 extravehicular activities totaling over 5 hours. He completed rendezvous and docking. And on Apollo 11, he was the lunar module pilot, second human to walk on the surface of the moon. And although he was not the first human to set foot on the moon and join the pantheon of great exploration first, he has earned a position of honor among scientists and engineers for his work on the practical application of orbital mechanics, rocketry, radar telemetry, digital computing, with a little bit of a dose of flying by hand, making the exploration of the moon and beyond possible. So the references I think are worth talking about. His thesis is available online. I highly recommend the next reference, How Apollo Flew to the Moon by W. Davis Woods. Excellent book, full of tremendous details. Also, the Mars Project by Dr. Werner von Braun has been reprinted and is available, as well as, of course, various Wikipedia articles and YouTube videos, especially from the FAA.gov. Thank you very much.
Oh, great.
Thank you.
Thanks, Chris.
All right, any questions?
Well, let's see. John Mixitz had a question about about satellites. And I'm not quite sure if you could clarify, John, what your question was about, how you get the satellites to a certain position, but I'm not sure what orbit you were thinking of when you asked that question.
Well, if I can kind of jump for a minute on that, you start off with your booster rocket, which lifts you off. And that's really designed to put you in a specific type of orbit, usually about 100 miles to maybe 150 miles. And then you have a secondary, engine or rocket that could bring you to whatever your desired orbit is. Getting to those geostationary orbits and the high altitude orbits, it's a lot of fuel, which is why the shuttle was such a popular vehicle. It was like bringing a pickup truck, so we could get to those altitudes and park a satellite. So that's sort of how the process works to get to different orbits. And again, changing the inclination is really can be an expensive maneuver.
And Ed had a comment. Said, thanks, great deal of information. While a bit over my head, honestly, I had no idea how involved Orbiter Rendezvous was and did capture a better understanding. Nice job.
Good. Thank you. That struck me as well. I really didn't realize the complexity of this.
Yeah, it really is complex. And, imagine, you were talking mostly about Earth orbit and traveling off to the moon. Well, some of these trips off to other planets are much more complicated, far more complicated than those orbits. And imagine the incredible accuracy that they're able to achieve. For example, you think about the New Horizons mission out to Pluto, and here you are sending a spacecraft out, something like 4 billion miles away, and you're able to hit your target within a few miles, and it's just incredible. So it really is complex, but they make it look easy. So,
if we have a moment, I did have a couple other slides that I didn't include in the first go, but I thought you might be interested if to have some fun. There are some orbit simulations that you can purchase. One is called the Kerbal Space Program, which is designed for Xbox, and these are the little Kerbals, and you plan missions, and I haven't used it. I don't have Xbox, but I did read the reviews on it, and it's pretty well thought of. Another one is called Re-Entry, which is also an orbital simulator, and I just heard about this NESSP orbiter, but I haven't looked at it. So here, if you want to, try your hand at maneuvering, this could be a little bit of fun.
Yeah. Cool.
I've tried these sorts of simulators, and they are wickedly difficult.
Yeah.
I tried a simple one, and it's very easy to get into an escape orbit, where, you become hyperbolic and you just head way out into space. So you see that sometimes a little bit goes a long way.
That sounds like a bad day.
Yeah. Yeah.
Great. Well, thank you very much, Chris. If there are no other questions, we can move on. Next up, we've got Mark is going to give a little overview of what's visible in the nighttime sky right now. And so, Mark, if you want to take over.
Sure. Do I have the ability to share the screen, or
You should be able to.
All right. Cool. Oh yeah. Let's give it a shot. All right. Slideshow from the beginning. There we go. Okay. So what's in the October night sky? So let's start with your constellations. Most of your summertime constellations now are heading off. They're setting in the west. Hercules, Sagittarius, Capricornus, even Aquila, they're starting to get lower in the sky. If you're going to do any viewing, you want to do it early in the evening. Most of your early autumn constellations like Pegasus and Aquarius, Pisces, they are either in the south or relatively overhead. And the one thing to say too, the asterism of the summer triangle is still quite viewable, though compared to the past couple of months, it's moved off from the zenith and is starting to head towards the west. Your late autumn constellations or early winter constellations are now rising in the east, like Taurus and Auriga. Cassiopeia is high up near the zenith right now. So all these, if you grab a pair of 7x35 or 7x50 binoculars, it might be nice to scan around and find some star clusters in here. So we're doing pretty well with planet viewing at the moment. We still have Jupiter and Saturn, though they are pretty low in the southwest right now. So this one over here is Jupiter. To its left is Saturn. If you start viewing early in the evening, they're still high enough to see detail right after sunset. So you can still see the cloud belts, the moons, and the rings of Saturn, and some of its moons as well. But the star of the show for October is Mars. Mars has been putting on a really good show for us. Yesterday was opposition, and I believe the 6th was the closest approach between Earth and Mars. But all this month, get out as much as you can. Preferably, later in the evening, 11, 12, 1 in the morning. That's when it's highest. That's when you'll get your best views. It is much higher up. So here it is on the star chart. Notice it almost looks as big as Jupiter, and it's because it's so close to Earth that it looks that big. In reality, it's only about a third of the size of Earth. But right now, it's hanging around in Pisces at the moment. So what do we talk about oppositions? This is an interesting little graphic. So here you have like a very bad model of the solar system. Everything's not to scale here, but it's good for the purposes of what we're about to talk about. So here's the sun, here's the Earth, here's Mars. And when they talk about opposition, Mars is literally behind the Earth right now, when it's directly in line with the sun. So when the sun sets, essentially Mars is on the eastern horizon, rising up. Just to, for a reference point, if you notice here, Jupiter and Saturn are kind of on a 90-degree angle. It's called quadrature. I'm not sure if it's exactly at quadrature, but it's close to 90 degrees. So when Kevin and I were looking at a video of Saturn, we made a video actually. You can actually see the shadow of Saturn casting a little bit of shadow to the left on one of its rings. But this just gives you some scale. Out here is just basically what you see in the nighttime sky, Mars superimposed, because it's, you know, it's closer to us obviously than the background stars, but this is how you're seeing it. And same with Jupiter and Saturn in between Sagittarius and Capricorn. So when we talk about opposition, not all oppositions are created equal. We just passed, we're on the downtrodden side of this cycle right now. Mars, the best one of the cycle was 2018. However, it was very low in the sky, so you had a lot of atmospheric turbulence for our latitude, and there were dust storms. This time, however, there aren't many dust storms to be seen, and it's much higher up in Pisces at the moment. So this time around, Mars is actually putting on a much better show than it did in 2018. And it won't be this good again until 2035. The next oppositions that are coming up, you can see that it's much smaller. Right now, it's 22.4 arc seconds. It's the diameter at closest approach. 2022, it's only 17.25. It's only 14.5. And 2027, only 13.5. So get out and observe it now while you can. So this picture here was taken by NJAG member Terrence Baz. This was through his C8, and it was on AVX mount. It was an SE C8 on an SE mount with a ASI 224 camera. Nice job. This was actually the night of closest approach for me. This is a sketch through my 14-inch Dobsonian, about 300 power. So what I'm sketching here is pretty much, or as close to you could possibly see, what you actually saw through the eyepiece. I actually sat in my astronomy chair and sketched all this. You can see Ceteris Major and some of the other lava fields. And over here too, Al Karsich was actually talking about this, what looked like dust storms were the atmosphere on the side here. So you actually seeing some small clouds. Uranus and Neptune are also visible now. They're very small, but they do betray their themselves compared to the background stars. They do not twinkle. So Neptune is hanging out here in Aquarius, and Uranus is in Aries at the moment. Our moon phases, good to know right now at this point. We are heading towards new moon, which is on the 16th. We're in a waning crescent right now. So if you're looking at any deep sky objects or meteor showers, right now is a good time to view them. In fact, we do have an upcoming meteor shower. We have the Oronid meteor shower. It's got its name from the constellation it appears to be coming from. The radiant is in Orion. Orion doesn't get up until later in the evening, so you want to view after midnight. The best night is the 21st, but anytime between the 20th and 22nd, you can get anywhere up to 10 to 15 meteors per hour. Dark sky sight actually helps as well. But you know, we do have a crescent moon, but it will set by the time Orion rises. So it's definitely a good time to go look. I'm going to go only through some of these just to save some time here. These are some deep sky objects that are visible right now. I also made a recording of this and put it up on our NJAG IO group. I will reshare it again. So everything you're seeing now is very similar, is also in that recording. So of note, globular clusters M13 and 92. You want to view them early because they're in the western sky and they will be the first to set. Your planetary nebulae, M27 and M57 in Lyra, as they are pretty high up, and you'll have them most of the evening. M15 is in Pegasus. It's right off the star Enif over here. And below it, there's another globular cluster, M2. The Andromeda galaxy is almost near the zenith right now. It's the best time of the year to view it in the early evening. And the Perseus double cluster as well. I'll go through some of these in some coming slides here right now. The Pleiades will be rising in the east. You might want to wait till a little later in the evening. That way it's a little higher up to view. So how do you find some of these objects? M13 and 92 in Hercules, and this is the keystone. This is kind of like Hercules' chest, and right off of his right side of his chest is M13, and this is, you know, what M13 looks like. It's a globular cluster. These are stars. These are very old stars, over 11 billion years of age, and they cannot escape each other's gravity, so they are stuck with each other. Planetary nebulae, so this is Messier 57 in Lyra, so it's kind of at the base of Lyra, the harp, in between these two stars down here. One of them I think is actually Sheliak, but I don't remember which one. And same, and over here you can see later in the evening, Lyra will be tipped on its side. If you have really good seeing, you might even be able to discern the white dwarf star at the center. Same with the Dumbbell Nebula. If you kind of make a line going through Vega, right through the head of Cygnus to Swan, Alberio, and go straight down, you can find the Dumbbell Nebula. That is also a planetary nebula. It's a little larger in size, quite a bit larger in size than the ring. And Cygnus, this is one that wasn't in the diagram, but right by one of the wings is the Veil Nebula. This is a supernova remnant. This is, again, another dark sky side object, and something you would want a light pollution filter, like an oxygen 3 narrowband filter, to view. Right off of, again, this is the Great Square of Pegasus. And remember that star Enif I was talking about before, you make a little diagonal jog right off of Enif and you find Messier 15. Again, that's a globular cluster. The only odd autumnal globular cluster that's easy enough to view. It's nice and high. So there's a couple ways to find the Andromeda galaxy. It is the closest large galaxy to the Milky Way and similar in size, and about 2.5 million light years distant from us at the moment. So, so if you go, you get the square of Pegasus here. One way to look at it is to go off of Alpheratz, go to go star hop to Muroc, make a right turn, and there's the Andromeda Galaxy. My favorite way to look for it is off of the W in Cassiopeia. There's a pointer star of Skedar over here. You just go, you scan over here with your binoculars, and you'll find the Andromeda Galaxy. Also of note is the great Perseus double cluster. These are also star clusters, but they're different than globular clusters. These are young stars. They basically used up all of their gas and dust from their nebular cloud, and they are slowly spreading apart from one another. So again, here's the W in Cassiopeia. And on autumn evenings, if you're looking north, it's kind of on its side here. And you'll just go straight down from Skedar and a little bit to the right here, and you'll find the double cluster. So a little bit of scanning, and it shows up in binoculars or a nice wide field telescope. The Pleiades M45, I always thought it looked like a shopping cart shape, like if you remember ShopRite from years ago. So they're also known as the Seven Sisters, and you can see them naked eye. Some people can see up to 7. Some people see less, depending on how good your eyes are. But that's if you look off of Orion in the late evening, maybe after midnight, Orion will be in the east, and if you go straight up through Taurus and the Hyades, you'll find the Pleiades. So that is it for me. I am gonna end the slideshow, and I'm gonna give back the screen to Kevin.
Okay, great.
All right.
Well, thank you very much, Mark.
You're welcome.
The sky. And what we're going to do next is we're going to have the business portion of our meeting. So we are going to end our broadcast on YouTube. So those of you who have joined us on YouTube, thanks for being with us tonight. Hope you enjoyed these presentations. Be sure to join us next time in November, second Wednesday of the month. Our next meeting will take place, and we'll have a talk all about the next mission to Mars. And so that, I think, is going to be really interesting for us to talk about. And so we hope to see you then. Thanks for